month, we had actually 3 lectures because last month, one lecture could not be held of some technical problem, that is network related problem, but that has to be adjusted in this month. So the format actually is like this. INAE is actually organizing with the help of other institutions. First, what we do that our participating institution, namely SOA, the OBC is actually present here, and we request actually Professor Chancellor Vikananda to say a few words about this lecture and this university for the benefit of those who are joining the first time this lecture. Mr. Nanda, would you like to?
Sir, good afternoon, sir. Thank you, sir. Thank you very much. I think I welcome Dr. Bhubaneswar Subhadi, the professor at IIT Goa, and all the distinguished members of INAE and faculty colleagues, and also students and participants, and Dr. Sharma, the coordinator. It's my pleasure to share a few words regarding the university. This is a university we started as a college in 1996, became university in 2007, and started with one college. Now it has 10 disciplines, multidisciplinary, including all medical science, dental science, faculty of engineering, management, social science. Recently, we have added veterinary science. Over the years, since we have focused on R&D, as a result, I think we are visible in the national ranking framework, and also INAE ranking framework, as well as also globally in QS ranking. We are this year we are in 16th position in INAE ranking as university category, and in QS ranking we are 800 to 2000 bracket. QS SCI we are 400 to 450 bracket. We have established over the last few years, I think, 16 research centers and 58 research labs. We have more than 1100 PhD students working in different areas, 1400 faculty members, and 40,500 students are working in different possible work, like research work, or undergraduate and postgraduate work in different disciplines. And we have a MOU with many top-notch institutes, and the university also has 191 foreign students and studying in different disciplines. And university is looking up like providing healthcare facility to the marginalized and to the privileged people in the vicinity. So recently the university has been NAAC accredited with the AAA+. Thank you very much. Thank you for giving me the opportunity to share our university.
Thank you, Professor Nanda. Now also, I'll request you one more thing, because you know Professor Subhadi well from NIT days, and it may be appropriate that you could briefly introduce our distinguished speaker, Dr. Subhadi.
Sir, the detailed CV I have not gone through because I'll just tell whatever I know about Dr. Subhadi.
That is enough. Please.
Dr. Bhubaneswar Subhadi, I think, is well known to, I think you also, sir, to me, right from 1986, when he was there pursuing his undergraduate study, then for PG, and also he was faculty there. We were colleagues together. And Dr. Subhadi graduated in 1988. Then he was finished his master's in 90, and then he joined as a faculty in IGIT Sarang. Then he went to University of Sheffield. If I'm not wrong, Dr. Subhadi, it is Sheffield or Manchester?
No,
Sheffield. It is Sheffield, no?
Sheffield.
Yeah. Okay. It is Sheffield for PhD, And then after PhD, I think he came back and he was a faculty in our NIT Rourkela. We were colleagues together, and I think we established the first one of the two center of excellence, first center of excellence in industrial electronics and robotics, where he was. We both together were there, and when I left, he took over the center. It was the center of excellence, and it was doing well. And over the years, I think he has published many top-notch publications, transactions. I heard that he has supervised 40 PhDs and more than 200 publications, and with all top-notch publications. And he has conducted many seminars, conferences, and also jointly supervised one of our faculty from SOA. He was awarded, I think, 2 years back, PhD, Dr. Satish Chaudhary, and he's also connected with our university. Besides, he's moved from NIT to IIT Goa, and he's doing extremely well. He was Dean Academic of IIT Goa, and he has contributed substantially to the growth of the institute and IT. And very much you are Dean of Academic and Dean of Alumni Affairs, also Dean of Alumni Affairs, also at NIT Rourkela. He has taken many new steps in NIT to promote to connect the alumni, and has done extensively well. I welcome Dr. Bidadar to this kind of the lecture. It is quite gratifying to listen to Dr. Bidadar, who has worked in various of fields, started in control, then moved to the photovoltaics, now in unmanned vehicles. So he has a lot of control. Is basically he has contributed substantially to the automation and control. So I think I might have missed many things, Dr. Bidadar. So I think he has a very strong CV. I think he can add if I have missed anything. Thank you, sir. Well, welcome, Dr. Bidadar, to our this lectures.
It is really a great pleasure to have Professor Bidadar Subudhi here. And I must also mention, he is not only a fellow of Indian National Academy of Engineering, he is also a distinguished alumnus of my alma mater, NIT Rourkela. Now, with these few words, may I now request Professor Subudhi to give his actual lecture. He is the right person to explain what it is. I am not actually from the control field or anything of that sort. I can't really comment, but definitely you have to listen to him to know something about the great works that he has done. Professor Subudhi, please.
Thank you, sir. Thank you very much. And it's a privilege for me to be with all my known and the peers of this society, particularly fellow INAE, to share some of my experience today. I thank Professor Nanda for introducing me, and I will just share my slides before I start. So is it visible?
Yes, it is visible.
Yeah. So let me just welcome all the my fellows to be here in this cyber platform. Today I will be sharing some of my research interest on navigation and control of marine vehicles. I will be covering some aspects on this ocean exploration and the different kinds of marine vehicles and navigation and control problem associated with these marine vehicles, and two problems of interest. One is path following control, the other is a formation control or a cooperative mission plan, motion plan. So that is necessary to deploy a group of vehicles for a particular task to accomplish, and some conclusions. So all of us know that the ocean covers about 2/3 of the earth and has great effect on our existence. Despite a lot of research has happened, but still many things are still unknown. And primarily our research will focus on the surface vehicles and aerial vehicles, but still this area of these marine vehicles on underwater vehicles is a very interesting area, because there are several questions are still unanswered. For example, how these biologically productive are these oceans, what processes dominate mixing between water and layers, and what is its total biodiversity, and the influence of Earth atmosphere, and how is it changing, and what are the consequences for human society. So these are some questions still to be explored. So therefore, there is a need of oceanic exploration. So basically what I mean this oceanic exploration means to study the physical, chemical, biological and geological phenomena that occur in the ocean and its frontiers. So therefore there are a lot of challenges before us for this oceanic exploration to accomplish, and the scientific challenges are many for this, and therefore we need to employ some kind of robots or vehicles, what we call as the marine vehicles or robots. I will come in my subsequent slides about the different type of marine robots or oceanic robots, or what you call also the ocean horses. So, and what are the technical challenges in controlling them, and what are the techniques needed to deploy at least one marine vehicle for a particular task, or how to deploy more number of vehicles for a group motion when we want to uh, employ them for a difficult task. So some of the practical application of the marine robots, if I can summarize that in science, environment, military, and mining, oil industry, and other applications. In sea floor mapping, and also the oceanographic and geothermal event, the response to know the response, and also for geological sampling, and for environmental studies, like for the long-term monitoring of the hydrocarbon spills, and how this water is being polluted, and how to know about this pollution, and about the environmental remediation, and also the to inspect the underwater structures, for example the pipelines, dams, etc. And also for there are several military applications, including shallow water mine and search and disposal, and submarine offboard sensors. Also in the mining and oil industry, we have ocean survey, resource assessment, construction and maintenance of undersea structures. And there are other applications of interest using these marine vehicles, like the sea hull inspection, sea tank internal inspection, nuclear power plant inspection, and underwater communication and power cable installation and inspection. So there are, and also underwater tours and fisheries, and not many applications are there by which the marine robots, the interest is more from the community of this control and communication and robotics. So to focus on the research on this area. And these are some of the examples of the marine robot application, for example, in defense, in the to explore the oceanic frontiers. And this is the Remus SOA, which is very famous and deployed by for the scientific missions by the US Navy mine for the mine countermeasure operations. And this is the figure that shows that multiple marine vehicles, we can put them in a formation to accomplish a task that is environmental mapping. And this is the application of a marine robot for pipeline inspection, and also geotechnical surveys, and also the aircraft, the marine surface aircraft can be used for the defense applications. So having said that, also there are very special applications so far the deep water hydrothermal vents are concerned. Particularly these vents are steadily becoming a major focus for the marine science and technology research, because there are potential, these are essential to know about the biotechnology, these are very much of interest to the biotechnological industries, and also to explore the mineral deposits in the vents. And but there are certain challenges in this study. For example, how we can map them accurately, and how you can pursue the geological survey, and how to monitor the biological and physical chemical activity at the vent and surrounding areas. and therefore it is a difficult task. If you look at the brain, there are a lot of the process can happen. And the other aspect is that to study about, to collect the bacteria, the study on the bacteria, and also to gas collection, and to know the details about the gas bubbles. So these are some of the activities of interest through the vents. So what usually is being done using the vessels, marine vessels. But as you know, these marine vessels are, they have poor maneuverability, and the coverage is less, and they involve high operational cost. So therefore, on the other hand, what is being done, we deploy some, divers for the purpose. But as you know, the divers is also, restricted. They have restricted coverage, and also we know that it is also sometimes it becomes dangerous, and also it becomes difficult to collect the georeference data through the divers. So therefore, there are a lot of technical challenges for these tasks to accomplish, and therefore, particularly we need some kind of study of the sensors and methods that we want to develop for data acquisition, the marine data acquisition, and to know about the signal processing and data fusion, and to how to disseminate this information. So therefore, there is a need of advanced technology, and that technology involves how to employ the autonomous underwater vehicles, or autonomous surface vehicles, or gliders, or submersibles, or vessels, etc., for these tasks to do. So the after these vessels, then slowly the movement has happened to develop these remotely operated vehicles. Just like it is basically the the inspiration comes just to, but these remotely operated vehicle, they have the umbilical cord, so therefore these are not truly autonomous. So you can control them somewhere from somewhere else, and it is fully actuated, meaning the number of degrees to control and number of actuators involved are exactly same. So therefore, all the degrees of freedom are easily controlled. So therefore, it is easy, but the still not autonomous. And the present trend is but this is very tedious again to control them remotely. So therefore, the next how to remove this control, from outside, and how to make it truly autonomous. So therefore, the new trend is to develop the autonomous underwater vehicles, where we want to remove this umbilical cord in the remotely operated vehicles. And these are some of the popular, the autonomous underwater vehicles developed over the years by several countries. I will give the complete the information in the next slides. And these are some of the marine vehicles. Those are called autonomous surface crafts. They they are deployed on the surface of the ocean. And as you could see that these vehicles have high maneuverability, and they have autonomy feature, and therefore the execution is not that tedious. And so this is the benefit of using the autonomous vehicles. Now the future trend is to use the sampling networks, where we can put these the divers and these vehicles, the autonomous vehicle, in a loop. So therefore, we can accomplish certain tasks, because this diver can also be supported by these autonomous underwater vehicles, or the ROVs, or the surface vehicles. And one such example that we can see, that the Martha's Vineyard Coastal Observatory in US, they have deployed the AUVs to monitor the episodic events. So this is the deployment of these AUVs and the sampling network they use for the particular purpose. But the key issue here is the communication and the information and also decision and control. So the communication, why it is an issue, because as you know that the underwater medium, this communication is very difficult because of the multipath propagation and the time variation of the channel and the low bandwidth and the low data rate. So therefore, for marine vehicles, the issue of navigation and communication is difficult to address. So therefore, when we design a control, so we must look into these communication aspects. So the future vision for these marine vehicles are concerned, like the autonomous underwater vehicle, we can put this surface vehicle along with the underwater vehicle and diver in a complete loop. So therefore, what we can do is we can set up a symbiotic link between the human diver and set of autonomous robots or the underwater vehicles or the surface vehicles. Now we can develop a multi-component, highly cognitive robotic system that can easily interpret, gather the data and interpret the data, and we can use it substantially at a later stage of time. So now the key motivation is that how we can ensure the diver safety and how the underwater operation we can achieve, and we can also go for several missions like the surveying of the seabed or the some of the mission plans, the underwater mission plans. So the autonomous underwater vehicles, a lot of research has happened in the recent years. As you could see that this is the development in US, and this is Ares, and this is the MIT. They have developed a underwater vehicle called Odyssey, and this is again by the US. And in UK this is Autosop, and Norway they are developing a lot of underwater vehicles, and that is called Hugin. And then this Remos again in US, and this is the Tetora in Japan, and this is the Marius AUV that has been developed in again US. And in India we have a couple of systems we developed like CMRI Durgapur, they have developed one. In Raurkela we developed two, and in Khodagpur also they are attempting some AUV development. And all these AUVs, as you could see, they have been propelled through thrusters, and they are also thrusters, and they are also capable of trajectory tracking and path following easily without any difficulty, because we can have both the control, the thruster plane as well as the storm plane control. So this is a very popular AUV, the autonomous underwater vehicle, where this automated underwater vehicle go wherever the people cannot, and also we can do a lot of weather data collection and other information by using this AUV. And also these AUVs are supported with thrusters and storms and ruders, and they are easily controllable for accomplishing a trajectory tracking control or a path following control task. So this is the remotely operated vehicle, which has no more of interest compared to, because the AUV is more of interest now because of the autonomy. So nevertheless, still some ROVs are used for some experimentation purpose. And this is the autonomous surface craft. They are also the one class of the marine vehicles. They are put along with this autonomous underwater vehicle for certain applications. And this is again developed in the AUV that lab that is in MIT, and this is in Stanford, and this is in Israel. So a lot of development has happened in these autonomous surface craft development, and the course controlling. But the problem here is how to control these surface vehicles, marine vehicle, the ASC, or what we call as the autonomous surface crafts. And the whole problem is that the sea waves and the ocean current or the wind, gust, and also therefore the proper design or suitable design of the path following control or a trajectory control is essential here. And this navigation control and of the navigation guidance and control, these three aspects are essential aspect for marine vehicles. and that can be achieved by using several building blocks, maybe different sensors and different actuators. And what we understand is basically the guidance, navigation and control problem associated with the marine vehicles. So we must provide some reference model, and we provide the then what exactly we want to design, the control design, and then the actuators, and we have the gyro and the compass for and all these sensors to measure the angle, and also to, in some cases, if some of the variables are not available, we can still design an observer and design a controller suitably. Of course, while we do so, we consider the effects of wind, and also the wind can be considered as a disturbance here. And this is the waypoint. When we provide this reference, the reference trajectory is the different waypoints are provided, and then the control, the motion control system what to develop. Then we have the control allocation there, and this is the surface vehicle where we consider the different disturbances like the waves, wind, and the ocean currents. And in some cases, as I mentioned earlier, some of them the variables of interest are measured by using some sensors, and wherever it is not possible, we can use some observers to design the controller. So basically, this navigation task is to direct the marine vehicle by determining its position, attitude, and course, and then to find out how it can navigate. So basically, what we understand by navigation, we are where am I? Currently, I am here, and I should know where should I go. So this aspect is basically navigation. So in terms of these marine vehicles, some interest here is that we have different variables involved here. Like we have the different linear positions and the orientation. And what we do is we need to know about different transformation of the coordinate frames, like the body reference frame to any other reference frame. So we have to convert it to the kinematics, and then we have to find the suitable control to achieve this desired orientation or desired positions. So then the navigation system we need to design by using different navigation algorithms, and this necessitate different variables like the linear position, linear velocity, orientation, and rotational velocity of the marine vehicles by some sensors we use for the purpose. So the navigation and control problem, basically what we want that the desired orientation, and this is the actual orientation. Our objective is that this error, the error from the desired, that is the desired minus actual, should be 0. So that is the objective. So how do you achieve this? That can be achieved by suitable control design. What you call so basically this control algorithm what you design, that must be put in a digital platform, and then the respective storm or rudder of the marine vehicle would be given the appropriate control signal to change the voltage of this this storm or rudder. So thereby we can you can control this heading or for this navigate, or you can have either a heading or a diving motion for a particular marine vehicle. So we can have this path following control, meaning it is a single path trajectory control. So where the actual path or actual heading, and then how it is the desired heading. So this is so then what is the visibility distance, and then what is the how to achieve this desired heading across the path. That is the objective, and we must design a suitable path following control to achieve this. So this mission control, for these marine vehicles necessitates different sensors and the navigation algorithms and the control, and how to do that, how to implement them in a computing environment, and then how to generate the appropriate propulsion or propulsive through the actuators, and so that the vehicle can navigate to a desired orientation or a desired path or a desired heading. So this is typically a UV structure if you look at it. So the AUV could be, the propelled either propelling through a thruster or a storm, and this is a very typical figure of a AUV, where we can say that this portion is called nose portion, and this portion is called hull, and this is the tail portion. This is the So what exactly we want? We want to control an AUV with some when there are disturbances, ocean currents are there, and all these uncertainties are there. So how to design the suitable path following control for an autonomous underwater vehicle? So therefore we need the fixed gain controller is not appropriate here. So what exactly we want? We want to develop some adaptive controllers. So all of us know the adaptive controllers are the gains are basically adjusted depending upon the change in dynamics of the plant. So basically our objective here is to design the appropriate adaptive controller so that it can so in case of any uncertainties or disturbances, the controller gains are adapted based on the estimated or the identified dynamics at every sampling time. So basically the task here is to estimate the plant parameters and states online, and thereby to, designing a control algorithm that facilitates the adoption of the gains of the controller. So, as I mentioned earlier, the marine vehicle control, we have several challenges. The challenges is basically in the communication. The communication, as I said, the communication in this the data rate is the underwater medium. The data rate is very slow, and also that and sometimes the data loss is also there. So therefore, we must design a control under this communication, and there is communication delay as well. So how to take care of that communication delay in designing a appropriate control, and also the disturbances like the wave disturbances, and so there could be the dynamics also, the AUV dynamics or the marine vehicle dynamics. There could be some parameter uncertainties, and there could be actuator saturation, and also when this problem becomes more amplified, when you employ more number of AUVs for some difficult application, and of course we need to ensure the endurance also. So one of the controller that is of interest to us and we designed for this underwater vehicle is a an adaptive controller that basically involves in identifying the dynamics of the underwater vehicle by modeling the dynamics through by considering a NARMAX model. NARMAX meaning nonlinear autoregressive moving average exogenous model. So like unlike the RMAX model, here the parameters are the polynomial is involved here. So what you do here, since the autonomous underwater vehicle is a very complex system, so dynamics is truly nonlinear. So therefore many there is a requirement that we must capture the dynamics, the nonlinear dynamics appropriately. And as we discussed earlier, that the adaptive controller is implementable when you will be able to know that this dynamics, how it changes at several sampling time. So therefore, at every sampling time, we identify the dynamics, that is the NARMAX dynamics, and thereby we design an adaptive controller. And the controller what we design is a self-tuning controller, that is one class of adaptive controller. And the approach we employed here is a line of sight approach, where we provide a set of waypoint tracking across a path. So the problem for the path following control over here is that we provide the path information, and then our objective is that our underwater vehicle or the marine vehicle must follow a desired path. So basically for that control to design, we must know the kinematics, and in the kinematics what we know, there are different degrees of freedom. Like we have the linear velocities, and we have the angular velocities and orientations, and these are the different degrees of freedom like surge, roll, pitch, sway, and heave. So what we do is we transform these variables from arch fixed frame to the body fixed frame by suitable transformation by this transformation matrices J1 and J2. So then the kinematics, these kinematics will be useful to operate these control with the body fixed frame. So what we basically um, intend to do here is that we want to identify the dynamics of this underwater vehicle, or what I mean that the nonlinear dynamics of the underwater vehicle at every sampling time by some appropriate suitable system identification technique. So what we do that we have the system. The system here is the underwater vehicle, and we choose different inputs, like what are the inputs and our set of outputs u and y, and based on these set of inputs and all these z to the power minus 1. So these are basically the lagged in the time delay, and then all these informations, these past information of input and past information of output of the AUV, that is yp minus 1 to k minus m, and the control inputs k minus n sampling instant time. So those informations are used to identify this mapping between the input space to the output space, and what by that, so basically the problem turns out to be a nonlinear function approximation problem, and our whole objective here is to identify this function f, or what I mean to say that every sampling time, if you can map this information, the input output information, we can easily identify the dynamics of AUD, or in other words, we can identify the dynamics of the Narmax model of the underwater vehicle. So our interest is to control the heading motion as well as the depth motion, and the heading motion involves the sway motion and yaw motion, that is the velocity and this the position, and then also the depth motion includes the heave motion and pitch motion, so that is W and Q. So involving these variables, we can identify the Narmax model of the autonomous underwater vehicle, and which we will be using subsequently for the path following control. So what you do here is that we choose a model structure, Narmax model structure. So this is the heading for the heading motion. We choose, this is the output, and the input is the rudder.
Sir, you are muted, sir. Sir, you got muted.
Yes, I got muted, and oh, just a minute. Now I am all right, but audio is not there.
Subudhi sir also got muted. Please unmute, sir.
I have unmuted, but I am not getting audio.
No problem, sir. I'm just asking about Subudhi sir also.
Yeah, now is it okay?
Yes, sir.
Is it okay now? Am I
yes,
audible?
sir. Yes, sir. Now you are
Yes.
audible. Sanat sir, are you able to hear?
Yes.
So which slide you are not? I am not audible. This slide I was audible.
Yes, sir. By this time you were audible. After that you were not.
Okay. So basically the purpose here is to identify two dynamics. One is the heading dynamics involving the sway motion and the yaw motion, that is V and R, and depth motion basically involving the heave motion and pitch motion involving W and Q. And therefore what we do, our purpose is to identify the Narmax dynamics of the AUV for the heading motion. So the V and RK are the outputs, and the rudder plane is the actuation is the input, and this is the modeling error, and we choose these are the polynomials f11, f21, and g11, g21, and these are the different constant terms in that polynomial. And for the depth motion identification, we choose W and Q as the output, and in the storm plane actuation, this is the input signal and this is the error signal, and these f12 and f22 and g12, g22 are the polynomials that describe this Narmax model. So our purpose is that to have a faster path following control. So for this path following control, we must if you consider here that the waypoint tracking, so we define different waypoints x1 y1, x2 y2, and x3 y3, and x4 y4. So every waypoint we also prescribe the region of acceptance, And then what you do is we consider a line of sight guidance. That means if you consider two waypoints, for example, ith waypoint and I minus 1's waypoint, and connect them by a linear approximation, then our purpose is to the path is now a linear path we want to track. So this is called the waypoint tracking using the line of sight guidance. Of course, we must consider the obstacle here, how to avoid them. So now coming to the design of the adaptive controller, what we have done, we have defined this path, desired path through the different waypoints, and of course we adopted the line of sight guidance control principle. And then what is our objective? We design a first we design a dynamic controller. So for this dynamic controller, we have two one is the rudder plane input and the storm plane input, and these are the different outputs, heave and sway motions, W and VW, Q and R. And then for these two motions, delta R with VW and ds with QR, and we identify the heading and diving motion, the Narmax models. And based on these identified models, every sampling time the controller gains K1 and K2 are adapted. And then once you do that, then what you do is we design a kinematic controller so that we can transfer to the this frame, the initial frame, to the body frame. So what we do is in the identification of this Narmax model, what we do, we write the regressors for this Narmax model, and for two motions, one for the heading motion and for the diving motion. And we employ a least square estimation, that is called recursive extended least square estimation technique, to identify the parameters of this Narmax model, like the constants that I mentioned in the polynomials. And this is the very popular the RLS algorithm, what is called the extended least square algorithm, where these are the previous sample instant parameters and the current sample current instant parameters. These are the updatation, and we have the covariance matrix, and this is the covariance matrix updatation. And we have this observed variable, that is y, and we have the residual error, and this pi, this is basically the regression. So using this method, we can find the unknown parameters, and thereby every sampling time we are ready with the Narmax model for these two motions that we are interested. Now to design the kinematic control, what we do, our purpose is to reduce the error. So therefore we design then we choose choose an objective function v1 that involves these two errors. That is one for the heading motion and one for the diving motion. Of course, here we have chosen to positive definite matrices R and Q. These are the weight matrices, and that so then our objective is to minimize this error. So then the error objective function we set is so if you substitute these values, you represent this ek, you calculate ek and E transpose k, and similarly the dk and D transpose k in terms of the different parameters, you get the objective function in this manner. So then we define these different errors, that is the what we call as the cross stack error. So that is basically that involves the path parameters and offset from the desired path. This is the dk. Meaning is basically the cross stack error. So our objective is to bring the dk to 0, and this is the different waypoint we prescribe, like I minus 1 waypoint, and this is the ith waypoint, and this is and we adopt the line of guidance control principle to accomplish this path following control. So once we do that, the kinematic controller, our next agenda is to design the dynamic controller, where, as I told you earlier, that we have two control inputs, delta, the rudder plane and the storm plane, and these are the corresponding inputs, and these are the gains K1 and K2 that need to be adapted. So these are the aerodynamics for the heading dynamics and the depth motion dynamics. And then what we do is we consider the V2 is another objective function that comprises of the error in the heading plane and the diving plane. And then this V2 we can put, if you put these values of R and Q, after substituting these values, you get the expression for V2 here, objective function. Now our total the net error objective function becomes for the kinematic controller V1 and for the dynamic controller K2. So then our purpose here is to minimize this objective function, of course with certain constants. What are the constants? As I told you earlier, the constants are basically with respect to the actuator saturation and with respect to the gain that what we would like to take. And these are the different Q, the matrix and C matrix we define, we calculated here. And this X basically the that involves the R and Q, the position and these velocities, and then also these the gain of the controller. So we perform a simulation to see that whether our controller is able to do the proper path following control. For that we choose a sampling time of 0.5 second, and we executed the simulation for 800 seconds, and we put these are the constants for the state and the actuators, R and Q less than 1, and the Kp values and the K1 and K2 values less than equal to 0.6. And these are the initial states, because the different, as I told earlier, that these are the linear positions and these orientations and linear velocities, and all of them we consider initial values to be 0, and this is our desired heading, we define like that. So then we make a simulation. In the simulation we could see we provided the dotted line is the actual, and the blue line is the the dotted line is the desired, and the blue line is the actual. As you could see, the head, this is for the heading angle control, and the heading error almost goes to 0. And then for the yaw velocity also we could see that the yaw velocity curve is here, the estimated yaw velocity, and also the rudder orientation is while tracking the desired signal. So what we do here is that, so this path following control to what we simulated, we want to verify it in real time. For that we develop a prototype on autonomous underwater vehicle. So then what we do, we have designed a a UV structure, and we selected the appropriate sensors, and then we also put the batteries here, and we have the like universal navigation system, we have the DC-DC converter for the power supply, and we have the different sensors like depth sensor, pressure sensors, and we have the Doppler velocity log and universal navigation system, and we have the single board computer and also the Atmega 2560 for the data acquisition, and this single board computer is used to we put the control algorithm here. So this is the this is the UV that has been developed in the lab, and these are the little about the different units. We have primarily sensor unit, computational unit, actuation unit, communication unit, and power supply unit. And in the different sensor we employ like the Doppler velocity log, INS, GPS, and depth sensor, and the computational unit involves the single board controller and computer and the microcontroller, and the actuation unit, the thruster plane and the control planes, and we have the acoustic modem, the DVL, the acoustic modem. And basically this INS that gives us the orientation and angular velocity, and the DVL, the Doppler velocity log, gives us the linear velocities, and the GPS gives us the XY positions, and the depth sensor also gives the Z plane motion. And these are the different sensors we employ, and the kinematics we can put here to transform to the body frame. And this is the so the single board computer, and we have the microcontroller. And what we do is we have used the robot operating system to integrate the sensors and actuator and the data acquisition system. And this is the representation of different sensors and computer nodes for the real-time implementation. And this is the thruster we have used. This is a brushless DC motor, and this is the DC motor. The control plane is a DC motor servo mechanism, and this is the acoustic modem used for the communication. And the power supply involves the battery bank that is same as the laptop battery like lithium-ion batteries, and DC-DC converter. And we have the integration of different sensor blocks and actuator blocks to this the control what you are developing for this path following control. So this is the implementation that we have the DVL, that gives us the U and V, and GPS is the that position as I told earlier, and depth sensor. And all these information we use a sensor fusion algorithm by Kalman filter algorithm to make this sensor fusion. And we have, this is the sensor unit, and there are two models we identified: the Narmax model for the diving motion, Narmax model for the heading motion. And these are the two inputs, W and Q, and the storm plane input. So this is the kinematic controller we design, and the dynamic controller. And this cost function, the error cost function V, is optimized by Mosaic, a optimization algorithm, online optimization algorithm. And this is the computational unit. And once you do that, then whatever PWM you generate, that voltage will control the torque for this thruster and rudder and storm. So this is actuation unit. So as I said, that the INS provides us the orientations and angular velocities, and DVL provides us the linear velocities, and GPS provides us the linear positions. Then we implement this path following controller in real time in this prototype, and what you get is that we get, this is the desired, the dotted line is the desired position heading, and this is actually the blue curve with the actual heading, and this is the heading error goes to 0. And these are the identification how they are converging to the stable values, and these are the updatation of the Narmax parameters, the polynomials, that is the constants in the polynomial, that is beta 0, beta 1, beta 2. So how they are converging to constant values. And this slide shows the control signal that is being generated in the rudder plane, and the computational time that is needed for generating this control signal. And this is the control, the computational time for the controller implementation. So, so what we do is that we compare the computational time if we take a self-tuning controller, and if you take only the relevant, the polynomials, not all the polynomials, that we call the minimum representation polynomial, and by that we can reduce this. If you see the computational time, so by choosing the constant adaptive controller, where instead of identifying all the polynomials parameters, only the the effective polynomials or the minimal representation if we make, so then the computation time can be reduced. So what we do is we verify this in a swimming pool for for demonstrate for the verifying this motion control. So this is for the heading motion. Yeah. So you also verified it for diving motion. So now, these are some of the algorithms for the path following control. But having done that, we also felt that we can extend the same for deploying a couple of autonomous vehicles in a group motion. So this formation control is a cooperative motion control paradigm, in which a lot of marine vehicles, maybe more than one vehicles, can be put in a group motion to do some particular task. And the advantage is that by putting these AUVs in a group motion motion plan, so you can minimize the number of sensors. And also suppose there is a, we want to have a survey for a large area, which is not possible for a single AUV, but now it can be possible to do the same. So, but for this task, there are a lot of challenges involved. For example, the collision avoidance. Even the second AUV or third AUV becomes the obstacle for the first one. Also, how to maintain the distance between them, or how to maintain the formation, and how to take care of the inter-vehicular communication. Of course, underwater communication is difficult. On the top of that, how to maintain this communication among these different AUVs. So what we did, if you look at this nature, like the birds flying in the sky, coming to the nest in the evening, so they are maintaining a formation structure. So that means one of the bird is behaving as a leader and rest are the followers. So this is called a formation behavior, that is the flocking of birds. Similarly, a group of fish, they are maintaining a particular group motion where one of the fish is behaving as a leader and the rest are the followers. So this basically, this group motion from the nature that inspires us to design a cooperative motion control or what is called formation control of autonomous underwater vehicles. And what you do is, so this coordination, so there you can either put the autonomous surface vehicle, or you can put both AUV in a loop. So the purpose is that they should be in a particular group motion to do some cooperative motion task. So in this group motion, so we extend this path following control. So let us imagine that in this path following, now let us say 3 AUV, or you consider in a group motion. So they are maintaining a formation. This is a triangular formation. And then we assign a particular speed that should not deviate, and they maintain a distance. This formation now a time, and there must be a distance between them, so that there should be no collision to happen. So that is the way we go for the cooperative motion control design. And one of the popular approach that is called leader-follower approach. That means one is a leader and rest AUVs are the followers. So either the path they can change, or some AUV can change the role also during this formation control. So for this, what we did is, but while doing this formation control of a group of autonomous underwater vehicle, we realized that there are some delays, the communication delays that is happening, and therefore what we do is this communication delay we estimate by using some delay estimator technique. And once you estimate the delay, then we extend that the previous NARMAX model-based adaptive controller for designing the same controller is designed here. Of course, here the kinematic controller is designed using a separate adaptive controller called backstepping controller. And our objective here is to have a formation control in presence of this communication delay. So basically, we extend the same method, and we only mention that the delay is how the leader states are communicated the follower states, and that is a delay, and how to compensate for that delay. So that is the objective here. And we designed this controller, and we could see that the different, we have considered 2 AUVs, and for simplicity, and because we have only 2 AUVs we developed in the lab, and we make an study that for a circular path, so they are maintaining, they are following a desired trajectory. This blue line is a desired trajectory, and the red one a leader AUV, and the follower AUV1, AUV2, and different controller we verified, and we are satisfied that this circular path is with a group motion, it is tracked. And this is the orientation. The orientation error, the desired orientation, this is the desired orientation, and the red line shows the leader AUV position orientation, and the green one is for the the AUV1, the follower 1, and AUV2 is the follower 2, and you could see that all of them are following the desired orientation. Of course, there is little deviation here, and this is the final. This another path we have, linear path we have chosen. The orientation we have chosen, and all of them are following the desired orientation. So the conclusion of this, this work is that we are able to capture the unknown dynamics, and also to minimize the, to reduce the computation time for the controller implementation. We have represented the, we adopted the minimum representation of the Narmax model by suitably identifying the significant regression terms, and we identified the Narmax parameter model by using the recursive least-square estimate estimation algorithm. And we designed the constraints self-tuning controller in the principle of line of sight guidance, and the actuation signals for the stern and rudder planes are generated that comply the actuator constraints and also the practical feasibility, and also the effectiveness of the controller is verified both in simulation, experiment, and also we have seen that how they are doing in this smaller AUV in a swimming pool. And this constraint adaptive controller also, we have considered the communication delay while you are extending the path following control for a formation control task. And despite the communication delay, you could see that the follower AUVs follow the leader AUVs and ultimately the desired path. And also the proposed control provides the bounded control action to avoid the actuator saturation. So still there are a lot of work we are expecting to take the challenge, like how to design the more effective the vehicle cooperative mission planning, considering the acoustic communication constraints, and also the underwater feature-based navigation, online target detection and identification, and data fusion, both the magnetic and the acoustic. And also we, while doing so, we must take into account the cost, and also the because one of the challenge here is that when you verify it, many times water goes inside, so the sensor may be, or the computational unit may be lost. So therefore, how to make it sure that how rugged it is, and how to prevent water coming to the AUV. So that is another task we are also focusing on. So we have been successful in establishing collaboration in this marine science technology with France, and we have participated in the Port Atlantic Research Cooperation Program, and we are executing our MOUs with 9 institutes in France, and I am now proceeding to France to conduct a special session on the navigation and control of underwater vehicles on 27 September at Brest, France. And these are some of the national collaborations, and we are collaborating with Bhubaneswar Limited to provide them consulting services on bathymetric profile and seafloor under sea clipping system and condition monitoring for their ropes used for the these ships. And also we are going for the CFD analysis for the hydrodynamic resistance on the ship model, and we are also suggesting them the non-destructive techniques for their ship maintenance. And also we are recently providing the consulting service to DRDO Hyderabad to design the optimized cooperative or formation control for multiple autonomous underwater vehicle, avoiding obstacles, and also how to implement the same in NVIDIA platform. And these are some of the references used for preparing this slide. And I must acknowledge, I must thank my PhD students Raja, Subhasis, Devrat, Viransi, Vikrandit, and Sabi, who have finished their PhD and contributed towards this research. I must thank my collaborators, Naval Science Technological Laboratory, Visakhapatnam, for providing this practical suggestions for implementations, and also visiting many times to their lab, and these people are coming to ours. And also with Plymouth University UK and Far Eastern Federal University, and also the sponsors like Naval Research Board for several projects, and the Indian government, the Department of Science Technology, and the Russian government, RMES and RFPR schemes, and Royal Academy of Engineering for supporting towards these issues. Thank you very much.
Thank you, sir. Thank you so much. Now, I would like to invite the questions from the participants. Please raise your hands or unmute yourself and ask.
Any question?
Yes, please.
Can you hear me?
Yes, please. I'm able to hear you. Yeah.
Okay. I'm not sure whether this question is valid one or not, but anyway, I will ask. If it is wrong, then you can tell me that. What I want to know is this underwater vehicle can be used to hit a target, either a ship or a submarine. Is that right? If that is so, what will be the ultimate error? See, supposing a ship is there, within what accuracy can you hit the ship ultimately? Will you definitely hit, or they call it an error radius. So will that radius be 500 meters or 100 meters or what? What is the value of that underwater vehicles that you are developing? Thank you.
For us, it is very small distance. It is only 2 meter for us. Only 2 meter. Depth is only for 2 meter maximum.
No, I'm talking about the error radius. See, sir.
Error.
The ship is there. You want to hit it, so you want to probably hit it at middle of the bow. So how much will your UAV may miss it? Totally miss the ship at all. So it may not hit it at all. So what is that error radius?
Actually, we have theoretically we have not considered more than that. Only 1 meter. As I said, the maximum region we have considered 1 meter radius. And in the swimming pool, of course, the practical limitation is there. We have not taken even that. We have taken a little less than that.
Okay, so at some point of time you will test this. Because in a sea there can be waves or very big waves, or something that is moving both the submarine and your UAV. Both can move from their path.
Yes.
You are taking half a second is your.
No. In that case, what happens? Suppose you are combining a surface vehicle and a vessel together. So they are maintaining some distance, safe distance. We calculate the safe distance, and we also make a pattern, like a triangular pattern or a trapezoidal pattern. In case there are more than 3, always make a triangular pattern is easier. So you can maintain a distance between them.
Okay, thank you.
Any other question? Hello, sir.
Yes, please. You are audible, sir. Kaushik Parida, sir. Yeah.
Hello, sir. Namaskar, Professor Sowadi. Thank you for your excellent and very interesting presentation. I'm Dr. Kaushik Parida. I'm an assistant professor at IIT Roorkee. Sir, I was wondering regarding the energy requirement of your devices. Like, for example, predominantly you're using lithium-ion battery for your autonomous underwater vehicle. So can you explain something on the, like, for example, do you find it there's a sort of energy requirement for your devices? And have you considered using self-powered, like, for example, generating energy while the underwater vehicle is traveling inside the water?
Yeah, that's a very interesting question, of course, but we have not taken into account all those. Maybe in future we can solar powered underwater vehicle we can also think of in future, and there are several energy options we have not explored all those. Our main focus on the path following and the formation control. Of course, energy aspect is very important, and that we will consider in future.
Okay. Thank you, sir. It's really an honor listening to you. Thank you, sir. Namaskar.
Thank you very much. Thank you.
Any other questions? No, sir. There are no raised hands, so we are come to the end of this session.
Madam, would you like to propose a vote of thanks?
Yes, sir. I will. I, Dr. Renu Sharma, host of INAE Distinguished Lecture Series organized by CSIR, IMMT and SOA. I thank Professor Vidyadhar Subudhi for such a lucid presentation on navigation and control of marine vehicles. Sir, beautifully controlled design for autonomous underwater vehicle, which is a challenging because of owing to the parameter uncertainties arising from hydrodynamic parameters and external disturbances due to the variation in oceanic currents. Sir, what you talk is extremely and extensively. You narrated about the modeling, control design, and real-time implementation of the control algorithms for underwater vehicles. You especially focused on kinematics for the body fixed frame, nonlinear dynamics of underwater vehicles, various design aspects, various control algorithm you had suggested, and we definitely look forward to work in this direction. And some of the suggestions which have been proposed by few of the participants, we would like to include in our future research also. Thank you, sir, for joining us at this event. I again thank on behalf of Shiksha Anusandhan University, IMMT and CSIR. Thank you, sir. Thank you all the in-depth esteemed participants present over here for joining this evening. Namaste.
Thank you very much. Thank you.
So, Professor Subudhi, do you have the your permission to share the recordings?
Yeah.
Okay.
Can be.
Good.
Yeah. Thank you, sir. Thank you very much.
I have actually another small thing, not actually part of this one. Please pardon my ignorance. So, supposing actually we want to use some sort of an underwater vehicle to monitor the condition of slurry pipelines. Slurry pipelines. You know, it is a multi-phase flow.
Yeah.
And of course, there will be number of bends also. We want to only think of that what is this level of corrosion or any place actually will it really give way? Because in slurry pipeline, this is a big problem. Is it possible?
Yeah, it's not possible. It is possible. It is possible.
So then what will be the problems?
The problem is basically it comes under the same thing, the depth control problem. The inspection, it has to put a manipulator on this, along with the underwater vehicle. It has to check the data there and bring the data for the, the inspection. So first of all, collection of data, I mean to say.
And plus, actually, the flow will be turbulent. It is not actually.
Yeah, that is a problem. That is a problem. Yes, you are correct, sir.
Right.
Yeah.
And
So
it is
it's a difficult problem. Yeah.
Not one time.
Yes, but still can be done because I have seen that couple of the Portugal University particularly, they have verified in the oceanic environment have the flow is of the high velocity. It is possible. We can do the same similar type of work can be done.
If something could be done, it will be very, very useful.
Yeah, definitely. I will see. I will interact with in more detail about this data. If possible, we can carry on because the whole problem is to implement in the reality. It involves a lot of investment to develop a AOV and all these components. For simulation, etc., it is quite easy. But when you put more than one AOV to construct and to implement, really it is very expensive.
Particularly in the slurry and oil pipeline.
Yeah.
Any type of actually malfunctioning that you find or there is a bust, it creates a lot of health issues as well as other issues.
Yeah.
That way it will be very, very useful.
Yeah.
Okay. Thank you, Professor Subudhi.
Thank you, sir. Thank you. Namaskar, sir. Namaskar.
Thank you. So thank you.
Thank you, sir. Thank you, madam.
Thank you, sir. So I officially stop the recording over here. Thank you.
Thank you. So may